So thank you so much for attending this talk. I actually come from sort of the domain expertise side and the application side, which is about actually using quantum algorithms and quantum computational chemistry to actually design materials. And this is really important for our company at OTI Lumionics because this is effectively what enables us to design materials very rapidly. One of our core principles, ideas, and philosophies is that new, novel, and exciting materials can help innovate and drive change for a customer or final product, such as things as like designing, things that you might actually interact with, such as a video game and how people actually interface with tablets. So one of our main product, and so to show that we're actually like a real chemical company, one of the main products and mainstays of our company is the cathode patterning material, which was designed as a request to basically embed the camera and under panel IR sensor underneath an OLED screen for a phone. If you don't know, in the OLEDs within your basically OLED phones, the light has to pass through a cathode. And this is particularly very problematic for IR radiation because the cathode will basically absorb almost all of it. This is why certain phones continue to have the notch. It's because your Face ID is very important. I'm sure some of you who have that continue to use it for banking, and it's a very secure system, but it's important that it is as accurate as possible. So it's not actually currently possible to embed this below the screen without OTI's technology. But technically you could design a material through guessing and checking, but OTI was able to design this material basically within and qualify it for mass production within 2 years. And this is because we have a very rigorous system and computational design, synthesis, application, pilot testing, and basically where we can rapidly prototype, design, and test materials within our domain expertise, which is within OLEDs. So basically, this material was designed as an initial concept computationally in early 2020. We basically had it within our own R&D facility by the end of that. Many different types of materials, basically it's, and we're able to test it. And basically by 2021, we were shipping out samples to customers. And by early 2022, they were actually testing it in Gen 6 mass production, which means kilogram scale material kept at, basically kept on an actual production line. And this is because we have taken the philosophy of having very tight integration between our various departments and how we can actually feed that information back into our computational materials discovery platform. We have actually a lot of people who work on synthesis, a lot of people who work on application testing, and a lot of people who work actually on the application engineering as well. And all this information is incredibly important in being able to design a material, especially when your end-use customer is very reluctant to tell you exactly what specifications they're looking for. But we're really here to talk about the computational aspect and why I'm so interested in quantum computing and why I'm kind of hopeful for the future of quantum computing is because when we're trying to design actually kind of any material and you don't necessarily own all the experimental data, any partner that you work with will be very reluctant to give you that experimental data. It's scarce and it's incredibly valuable to them. The other issue you could encounter is if you try to design a completely new material that no one else has ever designed before, and there's no experimental data for it. So all of a sudden, this idea of using artificial intelligence or machine learning to basically solve your problems goes out the window because you have no reliable data. So what do? You go online and you download Google's QM9 DFT simulation, basically produced database, and you try to use that. And then you encounter the problem that your chemicals that you want to design have 50 atoms, and the most they go up to is something around the neighborhood of 12 atoms. So you have to make your own database. Well, the most convenient method is to use density functional theory, and that's actually a very valid and reasonable method. The problem is that your machine learning and your AI algorithms have now learned very bad habits. Not only have they learned bad habits, they're going to add more bad habits to those bad habits that DFT inherits. And this becomes quite problematic because it's going to lead you to two circumstances. One, you're going to lead your synthetic chemists down the wrong path, or two, your synthetic chemists are going to start to ignore you. So this is why I'm so interested in high precision computational chemistry methods that are incredibly reliable. The challenge with quantum computing or at least that has been presented today, has been presented up until now, is that there is still not enough evidence to prove that a quantum computer is actually going to be helpful in reaching the full CI limit, which is the perfect simulation. There's still no evidence of that. And this is incredibly problematic because most of the systems that we have been simulating on quantum computers are classified as toy problems. And you can see here from this quantum volume estimation, we're looking at an astronomical number for systems that actually matter, or systems that we're interested in. And, even for simulating OLED materials, we want to be approximately about 250 logical qubits, because that's when we can use when we basically have a cast large enough where we've captured basically most of the electron information. So what OTI did, and starting in about 2017, is we actually went back and developed our own branch of quantum chemistry theory for quantum computers, which is called the QCC algorithm. This is basically a qubit native language for quantum chemistry on a quantum computer. And what we also did is we basically, in order to bypass the issue that a lot of quantum computers had, because we were working predominantly on superconducting hardware at the time, so we invented the iterative qubit couple cluster so that we could bypass the issue of non-full to full connectivity. But that still wasn't enough for us. So what we decided to do is we decided to build a classical emulator, which can basically run on thousands of cores, to basically answer the question, will a quantum computer potentially help us design new materials? But why did we start with the qubit couple cluster theory? Well, the first thing is that the unitary couple cluster theory was originally designed, or was originally invented actually for classical computers. It's a branch of, it's kind of a novel branch of quantum chemistry that was kind of came into existence around the 70s to 80s. And the idea was that because it has the name unitary in it, and quantum computers work generally on unitary operators, quantum computers must be able to do this calculation very well. And the answer is that no, they also struggle a lot to actually do this. And the reason is because the unitary couple cluster uses kind of these summation terms, which then have to be trotterized or qubitized. And the community has spent a lot of effort and a lot of papers in trying to bring that number down so that we can make more and more efficient circuits. So what we decided to ignore all of that and develop our own theory. So with QCC, we basically generate our entanglers in product form, so there's no qubitization, there's no trotterization, and we basically select the entanglers, whichever entangler is actually going to help us, meaning whichever one is going to minimize the energy to the targeted state. An interesting feature of this is the QCC always generates the minimal circuit set for your Hamiltonian. And the other interesting thing about QCC Hamiltonian is if you forget that you're simulating quantum chemistry, it will basically find your targeted state so long as you can define that targeted state for any problem that you can push as a Hamiltonian. And so, early days, we ran this on actually Rigetti's hardware when it was still very noisy. And we're actually able to get the thing to actually agree with the FCI limit for small molecular hydrogen. And you can see that basically this hydrogen only actually requires only two C0 gates. And the compression of this actually scales very well, meaning that comparatively to unitary couple cluster, QCC always will produce the minimal number of gate sets, especially when it comes to 2-qubit gate operators. But that's not necessarily enough. So with our emulator, we went out and we tried a conventional, strongly correlated quantum chemistry problem, which is the Chromium Dimer problem. And this is a problem which basically most people in the quantum chemistry community basically use their algorithms to tackle. And so this is basically your toy problem if you want to actually do something that is relevant to a chemist. So instead of doing a chain of hydrogens, all hardware vendors, all software vendors should be aiming to do Chromium Dimer, because it is a very, very difficult problem. And you don't get to basically pre-manipulate your Hamiltonian before it actually has to be simulated. Things like DMET, things like density matrix, or not density matrix, but RMD, those basically are not really feasible to do with Chromium Dimer because it will introduce error into your simulation. You basically made a trade-off. So we partnered with one of the lead massive cloud computing vendor who also provides quantum computing services, and they ran the algorithm well, first of all, Schrodinger, which is, I'm sure some of you know, estimated that this calculation with a cast of 2626, meaning that it would have, would take about 1,000 years to simulate on a quantum computer because it's considered to be that difficult. However, there are classical methods today, such as DMRG, which is a very well-known, a very well-documented, and a very good method to simulate strongly correlated systems. And we got a benchmark that was provided to us by a leading cloud vendor, which said that it would take about 10,000 hours, CPU hours. With the iterative qubit coupled cluster and perturbative correction, which we developed in 2000, we were able to basically do it in 100 hours, CPU hours, and get a lower energy. But the important thing is that one of the interesting things is that basically our method is very agnostic to any of the hardware, whether it runs on a simulator, whether it runs on universal gates, or whether it even runs on, well, there's a particular branch called parameterized quantum annealing, which we use, we've done a lot of simulations with Fujitsu and D-Wave on this, basically to do something which we'll talk about a little bit later about correction to the mean, correction of the quantum mean field. It's very good when you have multi-reference states that you basically need to sledgehammer and break open, because it can bypass a lot of the local minima within it. When you use something like parameterized quantum annealing, the challenge is that you don't always need it, and whenever you need it, you only usually need to use it once or twice. But the OTI's IQCC algorithm, basically it runs almost on any platform. So our quantum emulator basically can simulate up to 200 qubits as of right now. Can maybe 2 weeks from now, we'll simulate a little bit more. We keep pushing it every year as fast as we can, and basically one of the nice things about the emulator is that it is exact. It calculates the exact energy that a quantum computer would give you without any of the sampling issues. So this is the best energy you could get running these onsets on a universal quantum computer. And it basically can couple to any, we have means to couple it to basically whoever basically open sources their quantum kind of their quantum instruction sets, we basically can interface into them. So the first problem, since we're an OLED company that we're really interested in, is applying it to phosphorescent blue emitters. And this is a very difficult problem. It's very difficult for twofold. One, the accuracy requirement to design blue phosphorescent emitters is very high. You basically need to be within plus or minus 10 nanometers. The second is that simulating a triplet to singlet transition is not trivial either. These are states which they can have long coupling distances. Orbitals, which are spatially very far apart, can actually still be coupled, and there's no way of knowing this until you actually start simulating it. And the problem is that if you start going in the reverse direction, where you basically do the experiment first, and then you simulate it, you're not actually honoring materials, you're not actually doing materials discovery, you're basically kind of reversing this whole sequence. Density functional theory is currently kind of the standard go-to method for this. And there are actually density functionals which are specifically designed for these classes of materials. But there's, as we'll get into when we actually show some of the results, we'll show why density functional theory is not necessarily the best case when we talk about it from a materials discovery application. This error can be very frustrating for computational chemists and chemists alike to actually deal with. And so it's really important that we continue to focus on having very high accuracy and reliable simulations that reflect the physical reality in which these materials are basically what these materials are actually doing. So we went and simulated a couple of iridium phosphorescent materials, and then using many different methods and including some of the best DFT functionals, such as CAM B3LYP, and then we compared it to IQCC and IQCC plus perturbative correction. And so one of the interesting aspects was that, technically on, some of the best DFT functionals have slightly smaller average error. But when we actually think of it from a materials discovery standpoint, saying, if I have a material and I want to make a functional group change, which one's going to give me the best correlation? IQCC and IQCC PT outperform basically all the DFT methods. And this is really significant because it gives your organic chemists confidence that if they have one material as an example, they can use your simulation tool they can use that point as an anchor, which is not something that you can do with density functional theory. And we'll show you with another data set of more blue phosphorescent emitters, is that basically you can see this light blue line you get excellent agreement between the center line, which is supposed to show whether when experiment and simulation meet up perfectly. Whereas density functional theory, you can see a much wider scattering, and you can even see that it starts to deviate, meaning that it's not consistent with the experimental line. But one of the most recent things that we've been working on is we've been working really hard on actually deploying IQCC across many cores and developing an entire system that would be able to run in high-performance computing and code. And so this is an example of basically another blue phosphorescent emitter where we wanted to simulate it. And we were simulating 80 logical qubits. And I used IBM's Qiskit to get some of these numbers. And basically, you can see what IBM tells me is the circuit depth, and basically what IBM will tell me what is the runtime, depending on how many times I'm going to sample the Hamiltonian. And this is also assuming that we're using some heavy compression on the Hamiltonian. We can group commuting sets together. We can basically do a lot of other types of things to really bring the size of the Hamiltonian down. And you see that IBM has, and Qiskit has told me that this will take at least 47 hours. I don't think that includes the coupling time between classical and quantum hardware, but I can do this on on 8 CPU cores, pretty beefy CPU, nonetheless, basically within about 40 hours as well. So this leads me to show that while we are very optimistic that quantum computers will provide value because this is inherently basically an emulation of a quantum computer, from the hardware vendor standpoint, there's still a lot of work to do in order to actually make sure this matches agreement. But I'm very excited about this work because it means that we're going to be able to design new and novel materials incredibly quickly with very high accuracy. And, this is something which, we're more than happy to have conversations about partnerships or collaborations or whatnot. We collaborate with many academic institutions on application and fundamental theory in this. But, this is really where we think that, in the short run, what you could do today, tomorrow, 2-3 years before, while you're waiting for the hardware, there's no reason why you can't actually get really good quantum chemistry simulations done today. So thank you.
Can you go back to the sorry, I want to make sure that I understand what you were saying. So you're saying that essentially you can do this on a workstation in the same time that you will take for an 80 logical qubit quantum computer?
I would not say workstation because this thing does use a lot of RAM. To execute this simulation, you do need at least 120 gigabytes of RAM. I'm not exactly familiar that most workstations would have that access to that amount of RAM.
Okay, a large computer.
Yes, and we have done this on large computers.
So you see here from this data for the resource estimation, I can see that the CNOM is like 33,000.
Mm-hmm.
For the qubits, logic qubit, 80 qubits. So now, actually, we don't have, because of the noisy qubits we cannot run this even on the NISQ devices. So we have to wait until we have a very, very mature hardware. Now, if I will have to have this mature hardware, I can then maybe able to run quantum phase estimation where I will have exponential speed up. So where do you see the advantage here for this qubit couple cluster?
So the quantum phase estimation suffers dramatically from the barren plateau, and this is a well-documented issue. The other thing is that quantum phase estimation also, when you start actually going to really large materials, like this C0 gate count would be basically off the slide for a system this big. Whether this actually basically by that time, it is basically saying that VQE actually on a universal quantum computer may not necessarily be that efficient. But the question is, personally, I think that the quantum phase estimation will suffer a lot from barren plateau. So now you need a lot of compensatory methods around that, whereas QCC never has a barren plateau because it's always driven to the underlying solution.
I don't think quantum phase estimation will have a barren plateau because barren plateau is a problem in the NISQ devices, and it's depends on what optimization you use, if it's gradient based or not. Quantum phase estimation, we don't have this barren plateau. This is for the photon quantum computer, we use quantum phase estimations, and we are using advantage of this
Okay, that's new to me because I've seen way too many papers, including some recent by like John Preskill, which basically allude to that. There's going to be no computational advantage associated with phase estimation. So, I'm predominantly going by that research, right?